You've probably heard of quantum computing, but what exactly is it and what problems does it solve? I'm here with Heather West, Senior Research Analyst at IDC, as well as Serdar Yegulalp, Senior Writer at InfoWorld, to discuss and demystify quantum computing. Stick around. Hey everyone, welcome back to Today in Tech. I'm Julia Beauchamp, and like I said, I am here with Heather West, as well as Serdar Yegulalp, and we are going to really just dive into all things quantum computing today. So Heather, I'll start with you. I mean, I know this is, the crux of our conversation, but what is quantum computing?
So, well,
big question.
Well, first off, thank you for having me here. This is very exciting, and
yes,
love the topic. So here we go. So quantum computing is basically breaking out of classical compute, the way we think about it today, and using quantum mechanics and quantum physics for compute power that's going to enable us to solve bigger, larger problems than what we've ever been able to solve before in a faster, accelerated pace. And these problems are going to have a lot more variable, a lot more data coming into it. They're going to have more possible solutions. So we want to find the most optimized solution to the problems that we're going to solve. And when we talk about the difference between classical computing and quantum computing, the building blocks of both technologies are really different too. So for instance, with classical compute, we have a bit, 0 and 1, and yes or no, essentially. When we talk about quantum computing, we are thinking about a qubit as our basic building block. And so what's a qubit? A qubit differs from a bit in that it's able to hold the values of 1 and 0 and anything in between. And so if you think about the way your brain processes, your brain has all types of functioning and neural processes that allow it to function, and you're able to come up with all these possibilities. So that's essentially what we're doing with a quantum computer when we look at the differences between it.
Wow. How does that sound to you, Serdar? Any thoughts?
Sounds pretty intimidating, actually. By the way, thanks for having me too, because I've got plenty of questions that I'm sure that the enterprise folks in the audience are going to be interested in. Well, because the first one that comes to mind is that what you're describing is something that sounds completely different from the way a regular computer would even be constructed. So it sounds like in order to make a quantum computer, we have to go about it a totally different way than we would when we make a classical computing device. And that brings with it its own complications and its own difficulties.
Yes, that's exactly true. But it opens up the door to a whole new group of startups that are able to compete against big tech giants like IBM and Google, which we do have big tech giants, IBM, Google. They are developing their own quantum computing full stack machine.
I'm sure.
Yeah, but then because the fabrication of the machine, the quantum mechanics behind the machine, it opens up a brand new computing market to startup businesses, startup computing vendors, hardware vendors, as well as software vendors. Because if you have a quantum computer, that's wonderful. But if you don't have the software to be able to run the computer, to write the algorithms on the computer, to run the use cases, then you just have a machine. But it does offer some complexity because qubits are very unstable. And if you think about a qubit, if you think about like if you go into the office, if you're there by yourself, you can work, you can be really productive while you're in there. But the minute your office mate comes in, you want to chit chat, you slow down your productivity. So think about that as a qubit. Like the qubits, we need to have them work together or become entangled in order to process the information and be able to generate the results that we want. But the problem is that they're so I'm volatile. Is that a good adjective?
So the term that comes to mind also is fragile. And
fragile.
Once you establish an entanglement, it's very difficult to work with it because they have a very short shelf life, as it were.
Exactly. And in order to work with them, you need to run the machines at very low, we're talking like 0 degrees Kelvin, and even below that.
Oh, wow.
Degrees. So you need a cryogenic or dilution refrigerator in order to be able to stabilize the qubits long enough to process the quantum computation and then read the results back. And right now, that's kind of where we're at with quantum development is how do you stabilize these qubits? How do you reduce the error rates so that you can use the qubit long enough in order to get the results? And so it's a very complex, and as you can imagine, the skill set that goes along with having to maintain the infrastructure as well as to be able to program a quantum computer are very different than what classical computing hardware brings
Sure.
along with it as well.
I do, before we get super too forward facing, which is obviously going to be important, I do want to go a little bit backwards. And I was wondering, Heather, Serdar, maybe a combination of the two of you. Can you explain sort of how we got here, to the current quantum computing landscape? And then we can, look forward into the skills, et cetera.
Sure. So quantum computing, while it's becoming more mainstream and more enterprises are looking to adopt and start experimenting with quantum computing, the quantum computing development is actually in its fourth decade. So Richard Feinstein in the 1980s proposed that in order to mimic in a natural environment, you needed a machine that was part of the quantum, or not a quantum environment, but part of a natural environment.
Okay.
And so he challenged developers and researchers to start figuring out how can you build a quantum system. And since then, really in the labs, it's been this kind of scientific development, like what is a qubit? How do we develop it? What is superpositioning? What is entanglement? And so it really started back in the 1980s. And it's really, the reason for it is that there were these huge problems that just could not be solved with the compute power. And over the course of time, even though we have accelerators, we have all these other types of classical compute that are trying to increase the speed, there's only you can only go so fast,
Okay.
and we're running out of
It also sounds to me like there's a parallel to be drawn between the way quantum computing is now, the state that it's in now, and the state that conventional computing was right after World War II or so, where we had systems that were based on very primitive technology and that had very limited processing power and were built using components that were also very undependable. That they were fragile because they were of such new construction, and the principles weren't necessarily fully understood. But at the time, they still constituted an enormous breakthrough, and they pointed the way towards what could be accomplished when we could scale up and make things more dependable. So is that an accurate comparison?
Yes, the difference between the classical compute era that you're talking about and quantum is that now we have the cloud, and so.
Sure.
Back when they were in the 1940s or right after World War II, it was dependent upon the specialties that were inside the lab. But with quantum computing, it's actually opened up the door to an ecosystem that isn't just dependent on quantum hardware vendors and their specialists and the software vendors and their specialists, but there's these open source platforms and that have become accessible to the general population. So you and I could log in, go to either a vendor's quantum cloud site. We could log in, we could test it out, we could play with it. Now, we wouldn't have access to the most advanced systems, but we would still have access to the software development kits. We would still have access to some of the quantum systems or the quantum simulators, or there's what they call quantum inspired technology, so quantum annealers. And so basically what a quantum inspired technology is it's a computing system that uses the powers of the qubit, but they aren't dependent on the qubits interacting. And as a result of that the need for them not to interact. Instead, what they're doing is they're measuring the energy wave within the qubit. And as a result of that, you don't have the decoherence or the interruption that you would have. And as a result, you don't need to scale the qubits as much to be able to solve optimization problem, which is probably the most popular problem right now to solve using quantum computing or quantum inspired machines. But yeah, so we have these cloud options. And a lot of the hardware vendors, a lot of the software vendors from quantum, they identify that there are a lot of developers out there that maybe didn't get to go to college and work on computer science. Maybe there's just someone who's playing around. And so it's opening up this brand new world, this brand new ecosystem of developers. And it's really a lot different. And it's actually speeding up the development of quantum systems as opposed to the classical systems that took a long period of time to get
Definitely.
to where we are. So
Yeah.
This brings me to the next big question that I think Leah also had, which is what problems does it solve and what problems does it not solve? What are the specific things that we are trying to do with quantum computing that were not possible at scale before or were only possible at prohibitive scale?
So, to be honest, you and I probably will not have a quantum computer at our desk.
Okay.
The average problem that we solve,
Not for a few years.
but the average person probably won't have a need for quantum computer. The problems that we're trying to solve are enormous problems that just couldn't be solved before. And I mentioned climate change before, but other examples are personalized medicine. So being able to take different chemical compounds and use information from each individual person to make a personalized medicine. I mean,
Sure.
that's personalized drug. That's not something that we can do today. It's just way too much information, too simplified, or not too simplified. I'm sorry.
Too complicated?
Too complicated to be able to do at this point in time. It can also, right now, it's more optimization problems that are being solved just because of the scalability issue and where we are with the development. But as the technology as we're able to scale the qubits and have more qubits within the system, decrease the decoherence rates, and increase or quantum volume, the complexity of the problem that can be solved are going to increase. So, for example, we just went through a pandemic. Well, I don't want to say went through. We're
Actively in.
right. But with a quantum computer, a lot of the information that was coming worldwide, we could pull in. Where are the newest variants coming from? What are some of the new strains that we're seeing? What populations are being more affected? What's the mortality? Like all these different variables could come in, and this huge amount of data could be pulled in, processed, analyzed with a quantum computer. And as a result, we might be able to forecast that disease and how it's going to change and do a little bit more. So that's something that currently we can't do. But there are going to be problems that come from every industry. And right now we're seeing a big push with HPC centers adopting it because it's able to accelerate their compute power. But it's always going to be a hybrid. Like we're always going to see problems being solved with a hybrid approach using some classical and some quantum of some degree, because obviously we need to get it to the cloud, process it in the quantum cloud, and then bring it back again. So, and they're not a quantum cloud, but the quantum systems accessible via the cloud.
Okay. I think that...
See, that also points out... I'm sorry, go ahead.
I think maybe I think we might be about to say the same thing, maybe not.
Go ahead.
I was about to say, Heather, you pointed like this sort of hybrid approach. And I think that there's maybe like a misconception of like this quantum supremacy and like quantum advantage. So I was hoping that we could like demystify some of those terms. Is that what you were going to say, Serta, or were you going to say something else?
Actually, that's not a bad question to start with, though.
All right, then let's go with that.
The difference between quantum supremacy and quantum advantage?
And like what it means, and like are these sort of like hyped marketing terms, or is this like an actual like, I don't know, I guess industry term?
So quantum supremacy is the ability to use a quantum system to solve a problem that we've never been able to solve before.
Okay.
Or solve it faster.
Okay.
A lot faster than we've ever done before. And in 2019, Google had made an announcement that they had solved a problem and they'd achieved quantum supremacy. But later on, IBM responded to that, saying that their supercomputer was able to actually solve it once you turned on the right parameters of the computer.
Gotcha. So it was not necessary to use a quantum computer for that.
Exactly.
Okay.
And more recently, a group in China had announced that they had they had achieved quantum supremacy. But the problems that they're solving are not problems that would necessarily be of value to anybody. Random number generation. There we go. Sorry. So, I mean, that's great, but what does that solve? What value does that add? So we've kind of moved away from the term quantum supremacy and moved into quantum advantage. And what is quantum advantage? And basically quantum advantage is being able to use a quantum system to solve a problem or accelerate a process so that you get a business value, a scientific value, some sort of value to humanity. So it's actually using the system to do something, achieve some sort of value.
Okay. Then what were you going to say, Serdar?
I guess one good way to ask this question would be when we talk about the problems that are done exclusively or chiefly in the cloud with conventional computing, and then we talk about the subdomain of problems that is solved or accelerated with quantum computing. What's the big distinction? Is it because the things that we do in the quantum domain are things that have so many combinations of possibilities that conventional computing would simply be too slow by orders of magnitude? That seems to be the chief difference. Am I right?
I would agree with you. In the use of a classical hybrid approach allows for enterprises to kind of optimize their cost as well when they're using quantum, because obviously working in the cloud, working on a quantum system, there's a cost that's associated with using those systems in running those, executing those quantum workflows in the cloud. And so by, like you said, there's an exaggerated amount of answers or responses that you're looking for. But then what ends up happening is that you also have portions of those problems that they could easily run, and they can run in parallel. And so you don't necessarily need to send everything to the cloud. So you can optimize both get the most optimized answer for the problem you're trying to solve for those large number of variables or the largest number of outcomes and solutions or what have you. But then for the parts of the problem that you don't necessarily need, you can keep those running in classical, and you can optimize the cost that you're using to solve that, or you're accumulating to solve that problem. And in addition, you actually speed up getting to the solution because you're sending it to two different systems at that point in time. So,
sure.
The term that I was about to use that was on the tip of my tongue was parameters, the number of parameters that you have to take into account for when you were performing this calculation.
Parameters, yeah.
This is something that comes out of the machine learning space too.
Yes.
Okay. So I guess my final question, I think, on this specific theme of quantum computing is, how do you access it? Where can users go? I mean, business users certainly in this case, since you said, Heather, you and I are probably not going to use it. Maybe you, Serdar.
Right.
But what does the landscape look like right now for accessing quantum computing?
So as we've talked about, it's obviously the majority of it is going to be consumed through provisioned services or cloud services.
Right.
And we have kind of a few different options right now as to how you can get to those services. First, enterprises can work with quantum hardware vendors who have their own quantum solutions for a premium price, which in each vendor is different depending on how they're pricing it or what have you. And an enterprise would partner with a vendor, and then the vendor would give you access to their consulting, their quantum specialists, their quantum machines to help build quantum algorithms, quantum programs, and really help guide the organization's quantum initiative. Some enterprises and organizations are further ahead than others, and so it really depends on where you're comfortable. And when you partner with the quantum hardware vendor, you have access to those machines from that specific vendor. In addition, certain cloud service providers, such as Microsoft Azure Quantum and Amazon Braket, they provide quantum computing as a service solutions as well. But the difference between the cloud service providers in comparison to the quantum hardware vendors is that the cloud service providers have partnered with multiple quantum hardware vendors. And so when you access the quantum systems through their platform, you're able to get access to multiple vendors. And as a result, you not only do you get access to multiple vendors, but multiple types of quantum machines. So when I say that, the qubits, a qubit's just not a qubit. Like a bit's kind of just a bit, but a qubit's not just a qubit. So there's the quantum mechanics behind different types of qubits. There's a topological qubit and a spin qubit and a trapped ion. And basically it's what is the qubit material that you're using? It's an atom, obviously, but is it a superconducting atom? Is it,
Okay.
Is it a photon? And how do you isolate that qubit to be able to read the quantum computation off from it? And they all vary, but there's several different types that are under development. And so by accessing through a cloud service provider, you have access to all those, well, not all of them, but, a variety of different types, as well as the software development kits from each of those vendors. And then they're priced basically per run second. So
Okay.
that's kind of how we access it right now. So,
All right.
There seems to be a parallel between the way the different providers offer quantum services and the way they offer other things in the cloud generally too. Like if you go to Amazon versus Azure versus Google, each one of them has distinct, for instance, cloud native database services, and they're all offered to consumers with specific features that are exclusive to that cloud. Do you see something similar happening with quantum computing, that each one of these will have some differentiating factor other than just the toolkits?
yes. So when we talk about the problems that are going to be solved, now, obviously, the question is, when are we going to be able to achieve quantum advantage, and what system will make it there? And so one of the most popular questions that we get is, which system is going to make it there first? And
Okay.
and IDC, our team, we don't believe that it's necessarily a race to achieve quantum advantage. We think that over the course of time, the machines are going to continue to advance, and as you get more advanced machines, you'll be able to solve more advanced problems. And I think that's going to be the differentiator between each one. If you're looking to solve, for instance, right now, a lot of HPC centers are looking to adopt quantum computing application specific type machines, which essentially is the hardware that's co-built at the same simultaneously with the quantum algorithms, so that they can solve specific problems. But it's not going to be a general quantum computer where you can use it to solve one problem this month and next month be able to repurpose it to use it to solve a different problem.
This sounds very much like Google's tensor processing unit, for instance. They have very specific silicon to solve very specific problems.
Yep, yep. So currently that's what a lot of HPC centers are looking at, because they can exploit the quantum compute power that we have currently for their current to assist in their HPC problems that they're looking to solve at this point in time. So I really think the differentiator isn't necessarily going to be the software at the SDKs, but it's really going to be what specific problems will this machine allow me to solve? And I don't know that we really know that answer. I don't know that the vendors, they have some idea, but it's really going to be interesting to see how the next few years shake out, because a lot of some of the quantum vendors at this point in time have started to release their roadmaps to give enterprises some motivation and some visibility as to when they can expect to see machines with at least 1,000 qubits, and they can actually use them to start solving some of these problems.
Gotcha. I think that was a fantastic sort of wrap up right there. And I think we can leave it there because, we're also going to be discussing in an upcoming video about, we're going to dive a little bit deeper into some of the use cases, why invest now. So I think this is a good place to leave it. So thank you both so much. And thank you all so much for watching this episode of Today in Tech. If you like this video, you can give the video a thumbs up. You can also subscribe to our YouTube channel, IDG Tech Talk. Hit the bell icon so you're notified every single time we post a new video. I know this was a super complex topic, so if you have any questions, comments, just thoughts in general that you want to leave in the comments below, please do, and I will do my best to get back to you. Thanks again for watching, and we'll see you next time.